This is section 9.1, and this section is on sequences. So we start off with a definition. An infinite sequence of numbers is a function whose domain is a set of integers greater than or equal to some integer n sub 0. Typically, for sequences, n sub 0 is 1. There are special occasions when we don't start at 1, but for the sequences we're going to be talking about, most of them are just going to start at 1. We use the notation of a sub n to denote the nth term of a sequence. It's a way of kind of writing the formula that describes the terms of a sequence. So let's just dive right into it then and find the first 5 terms. Unless you're told otherwise, you should assume that your n sub 0, your starting value here, is going to be 1. So that means my first term is going to come from plugging in 1 for n. So my first term would just be 1 over 1. My second term would come from plugging in 2 for n. So that second term is going to be 1 over 2. The third term would come from plugging in 3, and so on. So 1 over 4, 1 over 5. So these are my first 5 terms. So again, this came from plugging in that 1, 2, 3, 4, 5 in for n. Okay, so let's look at another sequence. 3 to the n over e to the n. Once again, we're going to plug in starting with 1. We're going to plug in for n starting with 1, and yes, we do have to plug 1 in for both of these n's. So my first term is going to be 3 to the 1 over e to the 1. My second term would be 3 to the second power over e to the second power. And then 3 to the third power over e to the third power, and so on until we get to 5 terms. So 3 to the fourth would be 81 over e to the fourth, and then 3 to the fifth is 243 over e to the fifth. So there's my first 5 terms of that sequence. All right, let's go backwards from this. So now, rather than just plug and chug, I'm going to give you the terms of the sequence, and you're going to tell me what the formula is, or what the nth term is. Okay, so example 2 is going to go backwards. So we're going to find the nth term. So here's the first 4 terms. The square root of 1, square root of 2, square root of 3, square root of 4. I intentionally did not simplify these just to make it a little easier for the first example. I could have just written this sequence as 1, square root of 2, square root of 3, 2. But then I thought, okay, it's not going to be as obvious. So for this one, my formula, or my nth term, is the square root of n. Right? You plug in 1 for n, and you get this first term. You plug in 2 for n, you get the second term, and so on. So let's look at another one. 0, 1/2, 2/3, 3/4, 4/5. And I didn't put a dot, dot, dot on there, but these are infinite sequences. So let's talk about what the formula is for this one. Well, let's notice here that the denominator is 1 larger than the numerator each time. Okay, So maybe we say n over n plus 1. But then if we do that, and I start at 1, start plugging in for 1. So if I put n over n plus 1, if I start plugging in 1 for n, that's going to start me at 1/2. So how am I going to have to adjust it so that I start at 0? Well, let's subtract 1 from both of them. So we end up with, instead of n on the top, we got n minus 1. Instead of n plus 1 on the bottom, if I subtract 1 from there, I get n. So if I plug in 1 to start this, this listing out here, if I plug in 1, I'm going to get 0 over 1, which is 0. If I plug in 2, I'm going to get 2 minus 1 is 1 over 2. If I plug in 3, I get 3 minus 1, which is 2 over 3. So there's a certain amount of guess and check that goes with these, but there's also, just kind of looking for some familiar kind of patterns. Okay, let's look at another sequence. How about we take an easy sequence, like the constant sequence of 3's. What is the nth term? Well, the nth term is the same as every other term, right? The first term is 3, the second term is 3, the third term, the fourth term. So it kind of stands to reason that the nth term is going to be 3, not 3n. Be careful here. If you put 3n, now you're talking about the multiples of 3. 3, 6, 9, 12. We're not talking about the multiples of 3. It's just always 3, no matter what number you plug in for n. This next one is going to be a little different than the others here. So 1, negative 1, 1, negative 1, 1, negative 1. So it's just an alternating sequence of 1's and negative 1's. We have a lot of alternating sequences that show up in this chapter, so we need to be able to recognize the formula from which these come. All right. So the formula for this is negative 1 to the n plus 1. So notice if I plug in 1 for n, I start with negative 1 squared, which is a positive 1. Then negative 1 cubed, negative 1 to the 4th, negative 1 to the 5th, and so on. So the even exponents on negative 1 are positive, the odd exponents are negative. Now, something to note for the future, if you have negative 1 to the n plus 1, it's going to alternate starting with positive and then negative, positive, negative, and so on. Whereas if you have negative 1 to the n power, that's going to alternate starting with a negative. And there are sequences that start alternating with negatives. So if your negative starts your alternating, you're going to need an n power. If it starts with a positive, then you're going to use that n plus 1. You could always use an n minus 1 as well. Either one of those will work. So that's just kind of a general formula for alternating things. Now let's throw some alternating in with some other stuff. All right, so how about negative 1/4, 2 over 8, negative 3 over 16, 4 over 32, all right, so let's come up with the nth term. because those signs alternate, we're going to have this kind of thing happening. Sorry, one of these two happening. So this is how your signs are going to alternate. The other stuff, if you just look at the absolute values and you just have the 1/4, the 2/8, 3/16, 4/32, that's like the earlier examples. So we still have to kind of look for that pattern in there, but just know that the alternating signs will be handled by this part. All right, they alternate starting with a negative, so I'm going to use this -1 to the n. So my nth term is -1 to the n power. That will alternate my signs. All right. Now, how am I going to get the rest of this stuff? Well, let's notice what's happening in the bottom here. We got 4, 8, 16, 32. Kind of looks like it might be some, 4 times something, right? We got 4 times 1, 4 times 2, 4 times 4, 4 times 8. Okay, that's a little weird, so maybe it's not that. So maybe we come back to that. Oh, look, at the top, we just have 1, 2, 3, 4. If I ignore the signs, because I've already taken care of the signs. The top just being 1, 2, 3, 4, 5. Okay, that's not too bad. That's just n. Right? Because if I plug in 1, I get 1. If I plug in 2, I get 2. So let's come back to this. So that whole multiplying by 4 didn't really get us anywhere. But if you notice, these are all powers of 2. So 4 is the same thing as 2 squared. 8 is the same thing as 2 cubed. 16 is 2 to the 4th, and so on. So thinking of our starting number being 1, if I plug in 1 for n, I'm going to get this 1 on the top. Plugging in 1 for n is going to give me a negative 1 times 1, so that puts my -1 on the top. If I'm going to plug in 1 for n, I'm going to need that base of 2 to remain there, and my exponent is going to change, and it's always 1 more than the number I'm plugging in. So if my n starts with 1, I need a 2 there. So I'm going to take n and I'm going to add 1 to it. So let's test this out. If I plug in 1 for n, I get -1 to the first, that's a negative, times 1. So -1 times 1, -1. 2 to the 1 plus 1 is 2 squared. And then if you want to check it for, plugging in 2, 3, 4 for n. But yeah, these can get really, really messy. Okay, so where is this headed? Well, this is headed toward convergence and divergence of sequences. So let's look at some of those examples. Okay, so next up, our definition for what it means to converge and diverge. This is a very formal definition here. A sequence A sub n converges to the number L, because it's a limit, if every positive number epsilon, there corresponds a number n such that for all little n bigger than this big N, that the distance between the limit and the terms of the sequence is smaller than this epsilon. Now, what this is just like the super mathy way of saying that the terms of this sequence are all getting infinitely close to whatever this limit is. So, it's kind of hard to mathematically define what it means to be infinitely close. This is how we mathematically define that. Now, if there's not a limit that these terms of the sequence get infinitely close to, then we say that the sequence diverges. So let's look back at the sequences that I just did in example 2, and let's talk about whether or not they converge or diverge. So looking at first the square root of n. So what is this one going to do? All right, so we're looking at the terms of the sequence. The square root of 1, the square root of 2, the square root of 3, the square root of 4, and on and on. What are those terms doing? Are they headed toward a certain fixed number? Are they getting infinitely large without any kind of bound? Or are they getting infinitely small without any kind of bound? Well, one thing you can use to kind of help you visualize what this is going to look like is that we can, let me grab my calculator out here, we can use the function, the square root of x. Even though it's a continuous function that has all those in-between values, and this is just a sequence of just these discrete points. We can still kind of use that square root of x as a guide. So let me resume that. So that square root function is the top half of a sideways parabola. It is increasing. The y values here are increasing. They're just increasing really slowly. So as these x values are increasing without bound, those y values are also increasing without bound. So we say that this sequence diverges. There's no fixed number that you can say, oh, okay, the square root of anything never gets above this number. So we say that that's going to diverge. Let's see, B was this sequence. That was the n minus 1 over n. So the terms of that one were 0, 1/2, 2/3, 3/4, 4/5, and so on. That one might be a little easier if you put it in the calculator and you look at the decimals. You know, if you wanted to graph it and look at the continuous version of it, you could. So it looks like that. So can you kind of see that it really seems like it's got some kind of a horizontal asymptote business going on here? And it does. In fact, this converges to 1. So we write this little arrow to indicate that it converges, and that it specifically converges to 1. Now, how did I know it was going to be 1 without looking at the graph? Well, we're going to figure out here in a little bit in this section that we can use L'Hopital on this. That if you're going to look at this, you can say, hey, what is the limit as n goes to infinity of n minus 1 over n? A direct substitution here is going to give you infinity over infinity. So you can use L'Hopital and get that limit is 1. So just kind of give you guys a preview of how you can do these a little bit easier. C, that one was the constant sequence of 3. Well, those terms are super easy, right? It was just always 3. So it's going to converge to, you guessed it, 3. So it converges. D is this -1 to the n plus 1. Now, is it going to converge or diverge? This one's actually kind of tricky. Is that looking blurry or is that just me? Sometimes my eyes aren't good. This one's kind of confusing, all right? And this one's really tricky. You have to be careful with this one because The terms of this one, let's see, so because it's an n plus 1, it's going to start alternating with positive. So it was 1, negative 1, 1, negative 1, 1, dot, dot, dot. Does this appear to be going toward one number? No, it's just bouncing back and forth between 1 and negative 1. It's not getting infinitely large without bound. It's not getting infinitely small without bound. So would you say it converges to 1 and negative 1? No, it can only converge to one number if it does converge. So because we don't have a single number, we say that this diverges. And a little bit later in this section, we come across a theorem that says, hey, if you've got a couple of subsequences and those converge to two different things, then the whole sequence is going to diverge. So we're going to encounter this again. All right, and then lastly, from example 2, we had the sequence of negative 1 to the n times n over 2 to the n plus 1. This one looks kind of menacing, right? So my terms were negative 1/4, then positive 2/8, which of course reduces to 1/4, negative 3 over 16, 4 over 32, and so on. So what is this one doing? Well, it kind of looks like it's alternating, kind of like this one. And the signs are alternating. But while the signs are alternating, these fractions are getting smaller and smaller. So what this is doing is that this is approaching 0 by closing in on it. So we're getting closer and closer to 0 by bouncing back and forth on either side of 0 and getting closer and closer to 0 each time. So we go from negative 1/4, positive 1/4, negative closer to 0, and then we hop to the positive side, a little closer to 0. Then we're going to hop back to the negative side and be a little closer to 0. So we're just kind of like bouncing back and forth on either side of 0 and simultaneously closing in on it. So this one converges. Okay, so let's talk about how we are able to use L'Hopital's rule, because we saw that it can be incredibly helpful with determining what a sequence converges to. So let me write down a theorem for you that's going to help you to see how we can use L'Hopital. Okay, so suppose that f of x is a function defined for all x bigger than or n sub 0 for our sequences, that a sub n is a sequence of real numbers, and we're going to define it to where the a sub n, the terms of our sequence, line up with the function values at those n values, right? And here's the kicker. You don't even need them to line up for all of them. You just need them to line up for the end of it. Because if we're talking about where the terms are going toward, as far as like a converging, you know, where's the end of the sequence going, then we really don't care if it matches up perfectly at the beginning. We just need it to match up at the end. If that happens, then the limit of the function and the limit of the sequence are the same number. They're L. They're going to be different things because the sequence is going to be a set list. It's not continuous. The function could be continuous and have those in-between values. You know, our sequence, we're just plugging in 1, 2, 3, 4. We're not plugging in like a half or a third or anything like that. So we don't get those in-between values that we get with a continuous function. So this is going to allow us to use L'Hopital's rule. So let's look at example 3. If the sequence converges, let's find the limit. So what I'm looking for is the limit as n goes to infinity of this sequence. So I want to find the limit as n goes to infinity of the natural log of n plus 1 over the square root of n. If you think about like a direct substitution kind of a thing, we get infinity over infinity. Okay, so this has infinity over infinity form. So I'm going to use L'Hopital. That means I'm going to take the derivative of the top and the derivative of the bottom. So I'm going to get the limit as n goes to infinity. The derivative of the top, because it's a natural log, is going to be 1 over n plus 1 times the derivative of n plus 1, which is just 1. And then the derivative of the square root of n, that's going to be n to the 1/2, so it's going to be a power rule. So that'll be 1/2 n to the negative 1/2. So I'm going to clean that up a little bit here. And also I didn't really write that, I just said it, but I probably should write it as to why I was able to use L'Hopital there. Okay, let's clean this up because this is messy. Okay, so this is going to be the limit as n goes to infinity of 1 over n plus 1. Here I'm dividing, because that's what the big fraction bar means. So I'm dividing that by 1 over 2 into the 1/2. So see how the power rule, when I differentiated that, gave me 1/2 n to the negative 1/2. I just moved that negative 1/2 down there into with that 2. So dividing those two is the same as multiplying by the reciprocal of this fraction. So that's going to give me 2 n to the 1/2 over n plus 1. So all I did was multiply by the reciprocal of this, because that's the same as dividing by that fraction. Oh, Lord. Okay, so again, we get infinity over infinity. I'm going to use L'Hopital again. So the limit as n goes to infinity. All right, so power rule again. It's going to be 1/2 times 2, which is going to just be 1. And that'll be n to the negative 1/2 power over the derivative of n plus 1 is just 1. All right, now we're getting somewhere. That's going to be just 1 over the square root of n. The square root of n, as n gets infinitely large, this is going to go to infinity. So remember, 1 over something getting infinitely large goes to 0. So it does converge, and it converges to 0. If this answer had been infinity, then that sequence would have diverged. So it did converge, and specifically it converged to 0. Okay, so let's look at one where L'Hopital is not going to be helpful for us. So we want to determine if this sequence converges or diverges. So sine squared of n over 2 to the n. We're not able to use L'Hopital here because if I take the limit as n goes to infinity, this is going to infinity, but sine squared is not going to converge. So if you think about the sine function, it's just bouncing back and forth between 1 and negative 1. So sine squared is going to bounce back and forth between 0 and 1. So it's kind of hard to even think about whether or not this is going to converge or diverge, but because this is not going toward infinity. We can't get that infinity over infinity form. So we cannot use L'Hopital for this. But what we can use is a trick that we learned in Calc 1 that we have not seen in a while, and it is called the squeeze theorem. Okay? So the squeeze theorem tells me that I can squeeze this function between two other functions whose limits are easier to find. And if I can show that the two functions out here converge to some limit that's the same number, then this must also, because it's squeezed between there. So remember I said that the sine function bounces back and forth between -1 and 1. Well, the sine squared function's never going to touch -1. It's going to bounce back and forth between 0 and 1. Now, the bottom wasn't really the problem. The top, the sine squared, was kind of our issue here. So check this out. As n goes to infinity, this is just a constant sequence. This is just zeros, right? Because 0 over this, 0 over that, 0 over the other, it's always 0. So as n goes to infinity, of 0 over 2 to the n, that limit is 0. And the limit as n goes to infinity of 1 over 2 to the n. The 2 to the n is going to infinity. And remember, 1 over infinitely large is going to go to 0. So we have, so that's an and sign, not a plus sign. Because this goes to 0 and this goes to 0, and this is between these two for all values of n, because I know that the sine squared function is locked in between 0 and 1. So we say that by the squeeze theorem, or the sandwich theorem, you may have heard it called either one, so by the squeeze theorem, the limit as n goes to infinity of sine squared n over 2 to the n must also be 0. Since this is squeezed between these two, it must have the same limit as those two. So it converges. So I didn't write everything that I just said in there. You know, I could write a lot more and say, you know, by the squeeze theorem, since the limit of this, you know, lower bound is 0 and is equal to the limit of this upper bound, then, you know, that limit of that between stuff is also 0. Okay, so next up is something called factorials. Now, you may have seen the factorial symbol before. But the factorial symbol is a little exclamation point, and it represents an actual operation. So 3 factorial is the abbreviation for 3 times 2 times 1. So 3 factorial is the same as the number 6. 4 factorial then would be 4 times 3 times 2 times 1, which is 24. Right? 1 factorial would just be 1. And 0 factorial, you probably think it's going to be 0. You would be mistaken. It is 1. This is actually a definition, because we needed to define what 0 factorial meant. This definition shows up when we talk about like permutations and combinations in probability. But also, just to show you where this symbol is on your calculator, it is under the Math menu, and you have to go over to the probability, and you'll see it right there, number 4. So if you wanted 4 factorial, that would be 4 math, go over to probability, and then option 4. So 4 factorial is 24. So 0 factorial is 1. Oh, she tells the truth. Now you guys have seen examples of when factorials show up before. You just may not realize it, but when we start taking repeated derivatives of algebraic functions, we kind of, end up with this factorial stuff. So let's just talk about, I don't know, let's just pull something out here. If you were going to take the derivative of, say, x to the 6th, that would be 6x to the 5th. Right? Now, if you were going to take the second derivative, so the derivative of 6x to the 5th, so we'll just say the derivative of 6x to the 5th, that would be 30x to the 4th, because you'd have the constant multiple of 6, and then the derivative of x to the 5th would be 5x to the 4th. And then if you took the derivative of that, so 6 times 5x to the 4th, you would have the 6 and the 5, and then the derivative of x to the 4th, 4x cubed, and so on. So you can kind of see how this repeated differentiation, if we were going to repeatedly differentiate this down to 0, how that factorial would just kind of, show up in there. So anyway, just wanted to show you how you might have seen that creep up before. If you were going to simplify, a factorial expression, you can use your calculator. If you wanted to simplify something like, say, 10 factorial over 8 factorial, you want to be really careful here. Don't try to simplify 10 over 8 and then do the factorial. Instead, you could just use the calculator for both of these, or you could even do this in your head, because 10 factorial is just 10 times 9 times 8 times 7, all the way down to 1, over 8 factorial, which is 8 times 7 times 6, all the way down to 1. Because this is now all written out in terms of multiplication, I can cancel like that 8 with that 8, that 7 with that 7, 6, 6, all the way down here. And I get just 10 times 9, which is 90. All right, so factorials that are going to show up in terms of convergence or divergence. Factorials grow faster than exponential functions. Right? So we know that exponential functions grow faster than algebraic functions. But factorials grow even faster than exponential functions. Because of that, the limit as n goes to infinity of these two, so let's look at these two limits here separately yet together. Because the factorials increase so much faster than the exponentials, if the factorial's on the bottom, then the bottom's increasing a lot faster than the top. That whole fraction is going to 0. Here, the top is increasing a lot faster than the bottom. So that one's diverging because that whole thing is going to infinity. Okay, so I just want to show you also on the next page just how quickly those factorials are outpacing those exponential functions. So I'll be right back. Okay, so I just listed out the first, 10 terms for the sequence of 2 to the n and the sequence of n factorial. So this is, 2 to the first and 1 factorial, 2 to the second, 2 factorial. So you can see that it starts with the exponential function increasing faster, right? We got 2, 4, 8, and 1, 2, 6. But look at how quickly this gets out of control. By the time we get to 2 to the 10th power, we're only at 1,024, whereas 10 factorial is already at the 3 million mark. So this increases a lot faster. And it's not just 2 to the n. This would work, this would get bigger than 10 to the n as well. So any of those exponential functions, the factorial is going to increase faster. Okay, so let's go on to some definitions here. This next definition is going to be on the word subsequence. If the terms of one sequence appear in another sequence in their given order, we call the first a subsequence of the second. So I just want to give you some examples. So if you have the sequence 1, 2, 3, 4, 5, and so on, a subsequence example, there's a ton of them, right? An infinite number of them. One particular subsequence could be the odds, 1, 3, 5, 7, 9. Could be the evens. Could be the multiples of 5. Yeah. If my sequence is 2, 4, 6, 8, 10, I could have a subsequence of just the powers of 2 because all these are going to be even. Something you might not think about being a subsequence is if we have the sequence 1, 2, 3, 4, 5, and so on forever, that this is a subsequence. If you're talking about just kind of the end of a sequence being the subsequence, this is called the tail of the sequence. But okay, so if the terms of a sequence converge to L, so that's what that is saying. So this is the terms of a sequence converge to a number that we call L. So that's the way we write that. Then all of the subsequences are also going to converge to L. If any two subsequences of the same sequence converge to different values, then the original sequence diverges because there's only going to be one number that they should all converge to. And if any of the subsequences diverge, then the original sequence also diverges. Now let's look at this one specifically, because if we look back at that alternating sequence of 1, -1, 1, -1, one subsequence of this is just looking at the positive ones. That converges to 1, right? Just a constant sequence. Another subsequence is if I just look at the negative ones. Well, that subsequence converges to -1. Since I have two subsequences of the same sequence that are converging to different limits, my original diverges. Okay, more definitions. This is a long section. So a sequence with the property that the nth term is less than the n plus 1th term for all of the terms is called a non-decreasing sequence. Now, non-decreasing is just the fancy term for increasing or constant. Because you might just say, okay, if it's not decreasing, it must be increasing. No, it could be constant. Similarly, if the nth term is bigger than the nth plus 1 term, then we say that the sequence is a non-increasing sequence because those bigger terms are getting smaller, right? So the n plus 1th term is smaller than the nth term. Non-increasing is another way of saying decreasing or constant. A sequence that is either non-increasing or non-decreasing is said to be monotonic. So let's look at some examples and let's label them as non-increasing, non-decreasing, or neither. Okay, so this first one. The terms here of this 1 over n are all converging to 0, and while they're converging to 0, they happen to all be getting smaller along the way. So because they are decreasing the whole time, we say that this is a non-increasing sequence because it is decreasing the whole time. What about the alternating sequence of 1, negative 1, 1, negative 1? Well, this one gets smaller and then gets bigger and then gets smaller and then gets bigger. It's not strictly decreasing, strictly increasing, or constant. This one is a neither. This one, we talked about this one earlier. This one, remember by L'Hopital, is going to converge to 1. So these terms are getting bigger and bigger, and they're approaching 1. And they are increasing the whole time. So this is a non-decreasing sequence. What about a constant sequence, like just 5 over and over and over again? This one's kind of tricky because it does fit both definitions. It is non-increasing and non-decreasing. This one's actually both. So constant sequences are the only ones that have this luxury. So it's both non-decreasing and non-increasing. So constant sequences are the only ones that are both. And that's because both definitions that we had back here have this or equal to component. So both of them allow for there to be some constants happening in there. So it does fit both of those definitions. So we would say that 3 of these sequences are monotonic. So yeah, even this one is considered monotonic because it does fit the definition for non-increasing or non-decreasing. All right, the last thing is we're going to talk about bounded sequences. So we need, yes, even more definitions. Okay, some more definitions. A sequence A sub n is bounded above if there's a number, big M, such that all the terms of the sequence are below or equal to that number for all the terms of the sequence. If there is a number like that, then it's called the upper bound. So it's that largest number that the sequence never passes, right? Never gets bigger than. Similarly, it's bounded below if there's a number, and we call it little m, such that all the terms of the sequence are bigger than that value. So that term is less than or equal to this m here is below all the terms for all of the terms there. And that little m is called the lower bound. If a sequence is bounded above and below, we say it's a bounded sequence. So how are we going to find these bounds? Well, we're going to see with some examples that there are some kind of easy ways to identify these. So let's start with the sequence of n over n plus 1. You've seen this one a few times. So let's look at some terms. If I just start plugging in 1, 2, 3, and so on, I get that this sequence looks like 1/2, 2/3, 3/4, 4/5, and so on. This sequence converges. We think about the limit as n goes to infinity. This is infinity over infinity form. So if we use L'Hopital, we're going to get 1/1. This sequence converges to 1. Also, notice that these terms are all increasing. So because this is an increasing sequence, it's a non-decreasing sequence, the terms are going from 1/2 and they're increasing up to 1. So we can say that the lower bound of this sequence is 1/2, and the upper bound would be 1. Because it has both, the sequence is bounded. If it has one but not the other, then it would not be bounded. All right, let's look at another one. How about just the sequence n? All right, so that's just going to be 1, 2, 3, 4, 5, ... This sequence does not converge. This is just going to get infinitely large without bound. So it diverges. It does have a lower bound, though. Right? So it's got a lower bound of 1, but it has no upper bound. There's no number up here that this sequence ever just gets to and kind of stops. So because we have, one bound but not the other one, the sequence is not bounded. In order to be bounded, you have to have both an upper and a lower bound. Right. What about the sequence? We kind of keep coming back to this one. Got our nice little alternating sequence here. So that's going to be -1, 1, -1, 1, and so on. We know this diverges. We've shown this a couple of different ways. This diverges. Let's talk about the boundedness of it, though. Does it have a lower bound? Is there a lower number that this sequence will never go below? And yeah, we do have a lower bound. It's -1. Now, what if you were to say, oh, well, -2 is a lower bound because it'll never go below -2? You're right. We actually have things called like a greatest lower bound and a least upper bound, kind of like, your least common denominator. So you would be just as correct if you said, -2 or -5. It also has an upper bound of 1. So this sequence is bounded. So here's what we've seen. We've got a bounded sequence that we know diverges, and we've got a bounded sequence that we know converges. But then we've got one that diverges, a sequence that diverges that's like half-bounded. So is there some kind of relationship between boundedness and convergence or divergence? And yes, there is. So here's what we get. Not every bounded sequence converges. However, if the sequence is bounded and monotonic, it will converge, will always converge. So remember, monotonic was a way of saying that it was either non-increasing or non-decreasing. So if it's bounded and non-increasing or non-decreasing, then it's going to converge. So that's a really nice result for us. All right, one more example. So we're going to determine if this sequence is non-decreasing and if it is bounded above. So the sequence that I'm going to look at is going to be 3n plus 1 over n plus 1. All right, let's look at some terms and just see what this is doing. So if I just start plugging in, you know, n equals 1, n equals 2, and so on. So let's see, if I plug in n equals 1, I'm going to get, I'm not going to simplify these. So I'm just going to get 4 over 2, 7 over 3, 10 over 4, I'm going to get 13 over 5, 16 over 6, 19 over 7, and so on. So once I got the first couple, then I was just kind of home free. I didn't actually have to keep plugging in because I know that if I'm looking at 3n plus 1, if you think of this in terms of being a line, you know the slope is 3. That's your rate of change of 3. So look, this is jumping by 3s. This one was just going up by 1s. So once I, you know, kind of got going here, I was able to just kind of jump up my 3s. Does this converge? Well, yeah, because we can look at L'Hopital here, right? So you can think, what is the limit as n goes to infinity, 3n plus 1 over n plus 1. We know that that's infinity over infinity form. So if we use L'Hopital, that's going to give me 3 over 1, or just 3. Okay, so that converges to 3. Let's talk about the non-decreasing, okay? Because if it's non-decreasing, then it's going to have this upper bound of 3, and it would have a lower bound here of 2. It kind of looks like it is an increasing sequence, so a non-decreasing. If you can't just kind of see that, that's okay. You can always change these to be decimals if it's easier for you to kind of see what's happening here. That it's, you know, going from 2 to 3 here, and just kind of, it appears that it's increasing the whole time. But this is where things get a little dicey, because how can you tell that it's going to continue to increase from this 2 to 3? How do you know it's not going to increase for a while and then decrease and then increase and then decrease and then, just kind of end up at 3? Well, we got to do a little bit of work to get to that. For a lot of these, we've just looked at them and we've just said, oh, okay, look at a few terms and kind of hand waved and said, okay, yeah, that looks great. But to prove, to really like formally mathematically prove this, that this sequence is non-decreasing, we need to show that, and this is what's going to mess with you, okay? And I know it is an hour into this and you are not in the mood to be messed with. But we're going to need to take this sequence, this 3n plus 1, and replace n with n plus 1. Then we get this 3n plus 1 over n plus 1. We need to show that this inequality is true. Because, I'm going to dig back here through the notes. We said that non-decreasing meant that the nth term was less than or equal to the n plus 1th term, or the n plus 1th term was bigger than the nth term. So that's kind of how I wrote it with this one. So my n plus 1th term, I replaced these n's with n plus 1's. So is this inequality true for all values of n? All right, so what I'm showing here, again, I know I just said this, but this is the n plus 1th term. It's bigger than the nth term. That's how you know it's going to be a non-decreasing sequence, is if that's generic terms. We can't just say, oh, the 5th term is bigger than the 6th term, or is the 5th term is bigger than the 4th term, or the 6th term is bigger than the 5th term. You can't just say that. You got to say generically, does this always work for all these numbers? All right, so here's what we're going to do. We're going to do some algebra. So let's multiply all this out, clean it up a little bit. So we get 3n plus 3 plus 1 over n plus 2, and we're trying to verify this. So you could actually just kind of put a little question mark over there, but just to show you, hey, we're trying to verify that inequality. And that'll be 3n plus 1 over n plus 1. Okay, so that'll be 3n plus 4 over n plus 2. And we want to know, is that bigger than 3n plus 1 over n plus 1? If this is true, then these cross products here, this cross product is going to be bigger than this cross product. So that means that 3 n plus 4, that quantity, times n plus 1 would have to be greater than or equal to 3n plus 1 times n plus 2. So does that inequality hold? All right, let's FOIL all this out. So that's going to be 3n squared, 3n, 4n, 4. Let's FOIL this out. That'll be 3n squared, 6n, 1n, and 2. Okay, now let's do some comparing. So we got 3n squared, 7n plus 4. And then I got 3n squared plus 7n plus 2. Because these are the same, let's eliminate those because those are equal. And here's what we got. We have 4 is greater than or equal to 2. Is that true for all values of n? Yes, it is. So we have verified this inequality and said, yes, that inequality is true. So just like that, we are done. That means that 3n plus 1 over n plus 1 is non-decreasing. And then we said that it was bounded below and above. So it's non-decreasing with a lower bound of 2 and an upper bound. Oh no, almost out of room. It's okay. Of 3. So why did it have a lower bound of 2 and an upper bound of 3? The lower bound of 2 came from right here. We just showed that it was non-decreasing, so that means it's increasing or constant from 2 all the way to 3. Okay, so that finishes this section. So this concludes section 9.1.